thanks for everybody for coming. I'd like to tell you what I have been doing this, since I came to Townsend, right? Most of my time was dedicated to this. So, the title of my PhD is Advancing Conservation Planning for Persistence. And then I focus on Brazilian coral reefs, which makes more sense, even though the findings my work have done also are applicable elsewhere. So, to date, much of the effort to conserve the coral reef biodiversity has been done through the establishment of MPAs, or marine protected areas. So you all know that there are MPAs covering coral reefs everywhere in the world. And this last estimate I could find is 2006, paper published in Science, which accounts for 20% of the coral reefs being already covered by MPAs, almost 20%. Which means this is a lot. Maybe compared to other marine ecosystems, coral reefs are the ones who have invented, have been giving lots of conservation emphasis, right? For example, in the early 2000s, every year 40 new MPAs has been added to this global network of MPAs. However, we could assume that most of these MPAs have been failing to achieve their conservation goals because a huge body of scientific papers has been showing that actually coral reefs are facing a crisis, right? So you can see from one of these pictures, which comes from these papers, there is this shift from a coral-dominant state to a fleshy macroalgae state. There are also lots of coral disease outbreaks, which has been very well highlighted and documented by the literature. So these stressors, they range from local stressors, such as overfishing, and also includes superimposed impact global scale stressors, such as ocean acidification and global warming. So why then marine protected areas are not working? So there is really a problem here. So I have there are mostly three hypotheses for this misfit. One is there is a risk that marine protected areas have been placed right towards areas which are less promising for commercial uses, right? This is more or less copying which has been happening in the terrestrial realm, where most of the protected areas are actually further from where activities is happening, right? The second thing is actually the spatial coverage. It might be a misleading indicator of real effectiveness because there are many paper parks, as we also all know. And the third thing, which is actually I'm going to tackle in my PhD, it's this process. There are many, especially this is particularly true for the marine realm. There are many processes operating doesn't respecting the boundaries of the MPAs. And if these processes are not accounted for when you plan new MPAs, you might be then overlook lots of important things. So to counteract this ongoing biodiversity loss, one way, and one has been proved to be a robust way to deal with this, provide a better guidance, how then you're going to place new MPAs is using systematic conservation planning. So this, can be seen as a multi-step procedure where you have just 11 stages, which looks like a unidirectional flow of steps, but actually you might have some loops and feedbacks which changes the shape how you apply this in practice. The idea that you have just 11 stages which are grouped into 3 phases, the top, the middle, and the bottom level. So basically you scope your conservation plan, and then you collect data, you gather data and interpret those data, and then you eventually apply this on the ground or in the sea. I want to highlight 2 very important steps in this framework, which is, one, it's in the scope phase, you might have high-level biodiversity goals, and then based on the data you have, so you're going to interpret those data to then set up conservation objectives, right? Which is in this more analytical phase, let's say. Then just to keep in mind, we have these 2 very important phases, which actually is gonna tell us the progress you have been doing effectively, right? The benefits of applying this framework has been also highlighted by the literature. So conservation planning has been proven to provide real conservation outcomes, which means, for example, increasing species diversity, increasing some species abundance for the ones we might be more interested to conserve. There is also a better allocation of management resources. We all know there are some constraints when apply conservation actions, and then we might then optimize this allocation. We also make things more explicit and defensible because conservation planning deals with maps and a lot of decision support tools, makes the process more transparent. And we can also explore the implications of different scenarios. And then the last benefit is actually we also deal with the idea of minimizing the social ecological impact of the conservation interventions. As I mentioned in the beginning, so conservation objectives are really important because we can shape then what we want to track, right? Or which progress we have been making. Most of these conservation objectives in conservation planning are done by representation. It's one principle where the idea behind that is you want to capture a sample of the biodiversity of your planning region. For example, if I'm interested in a tropical seascape, I want to have a little bit of seagrass inside my network of MPAs, or coral reefs, or mangroves, and so on. But the idea is that actually, even protecting like a sample of a little bit of everything, I want to actually guarantee that my network is going to really work. So the idea is because conservation objectives has also to deal, and this is a challenge, with persistence. And when I mean persistence, I refer to ecological process, which underpin biodiversity, and also dynamic threats. We all know that the threats are expanding over time, and you cannot just use a snapshot of the threat as a way to incorporate it into conservation plans. So, when I say ecological process, I mean species interactions, migration of species. We know that conservation marine protected areas might have lots of fish inside their boundaries, so which means some ecological processes are happening, but we also want to make just MPAs, for example, sustaining catches outside their boundaries. When you're planning for then biological persistence, one of the most important ecological aspects is called its term connectivity, which is the movement of organisms. So the exchange of individuals among habitat patches. We know coral-reefs are inherently patch and fragmented. So there is a exchange of individuals via migration or juveniles and adults, but also larval dispersion. And connectivity is very important because it sustains lots of ecological and evolutionary process, and also the level and the condition of connectivity has been altered by human stresses. For example, when the coastal development increases the fragmentation of coral reef habitats, and also when you overharvest some fishes, you might also make the connectivity weaker. Between all the ultimate threats, the one we cannot control very much, what's happening inside the MPA, climate change is the most important one. Because it's the one managers has the least control about the root cause, right? So, for example, even if I manage it very well, when I try to control and I have some management interventions in the catchments, I still might have bleaching happening in my MPA, which is not desirable. So, this is particularly important for coral reefs. We all know as well coral reefs are very sensitive to climate change and respond quite remarkably. So then this comes to the overall objective of my thesis, right? My thesis aims to advance conservation planning for biological persistence through improving the integration of connectivity and climate change into marine reserve design. So I gave you a little bit of the background, which is this general introduction. This is the overview of the thesis itself, and then I'm going to introduce you a little bit more about coral reefs and give you an overlook about the conservation status of these reefs, and then I provide a framework for setting persistent related objectives, and then I do a plan for connectivity, a plan for climate change, and then I interact, put all together in my chapter 6, and then I give you some final considerations, which is my chapter 7. So this is when I'm going to give you a little bit of the idea about the status of coral reefs in Brazil. So this is the paper entitled Analysis of Progress Towards a Comprehensive System of MPAs in Brazil. This was published in 2013 in this Journal of Nature Conservation. And the idea, the objective was to undertake a gap analysis, I'm going to explain what it is, to investigate how well MPAs then meet some design criteria for the coral reefs, while representing broad delineation of coral reef ecosystems. So, Brazilian coral reefs are then located in the western Atlantic Ocean. Here, all this coast, it spreads along 2,000 kilometers. And we have many reef types. There's one atoll, some oceanic, fringing with bordering oceanic islands. You have near-shore banks quite far from the coast. Although you have a low number of species, the endemism level is quite high in terms of area they occupy. And then, to explore more, to give you to investigate, right, how well MPAs are protecting Brazilian reefs. So I did this gap analysis where basically the idea is to identify areas with high conservation value which are underrepresented or they are outside any MPA. So to do that, I built a habitat map, right? And then I overlay with a management map, which is basically the boundaries of my MPAs, and then I identify my gaps. Areas which are overrepresented, maybe, and areas which are underrepresented. So I stratify my coral reefs according to the boundaries of ecoregions. I have 4 ecoregions in Brazil, according to this gradient of color. And then I intersect this with my map of MPAs. So I divide my MPAs into 2 types, basically. No takes, which offer full protection, and multiple uses, the one which are more flexible, so allow some constructive uses, but better than outside their boundaries, right? So I did this intersection, but within each ecoregion, I also evaluate the size of the no-take areas, the distance between, so to calculate the spacing between MPAs, and also how many replicate. So for each reef type, how many examples of them are contained inside separate no-takes. So I give you some results. This is a spatial coverage. Following the global pattern of protection of spatial coverage of MPAs, I have a highly, a huge amount of my Brazilian reefs are actually inside already MPAs, as you can see from this pie chart. So the coverage, it's quite high here in these 2 ecoregions and also in the little bit to the south. You just have a lack of no-take areas in this northeastern coast, but it doesn't look that bad. So I could maybe stop my PhD here and say, maybe go home. But no. So let's have a closer look at what's happening actually. So when I measured my spatial design, when I look at the spatial configuration of my no-takes, I see, for example, then there is the size of the space of the no-takes range, the range is quite great, from 1 to 850 square kilometers, for example, but the majority of my no-takes are actually very small. And the spacing as well between these no-takes is quite high, so it's 150 kilometers. When I check this with the best recommendations for the literature, I can see that actually they fail, right? Because the size, the minimal size recommended, it's 10 square kilometers, and I have like half. My spacing should be maximum 15 kilometers to guarantee, for example, assuming to guarantee connectivity, and actually I have my spacing mostly 10 times bigger. And the replicates varies from 1 to 3, so it's not that bad. But then, like I say, okay, we have this pattern. So the spatial configuration is not the best, but they cover a lot of area. So it's definitely well covered, right? Let's then have a look, like I mentioned before, to see then more in depth if it is actually it's closer to function, to be functional, right? To do that, I started providing this framework. So this is my data chapter 3, or chapter 3, data chapter 2. So integrating connectivity and climate change into marine conservation planning, right? Here, this was published in Biological Conservation 2014, and then I investigate then the extent to which connectivity and climate change have been considered in an ecological meaningful way. So now let's check, let's see what's happening when I have the best ways to deal with this process. Here I went to the literature review. I reviewed 115 marine planning studies addressing connectivity and 47 addressing climate change. So this includes grey literature, like reports from NGOs and governmental agencies, but also peer-reviewed papers. And then I extracted in a database 329 recommendations for connectivity, 202 recommendations for climate change. I collect this all in this database, and then I try to identify trends, patterns, or how then I could better deal with this process. I also classify, because I found the range of approaches or recommendations is quite high, so I have to classify all these recommendations, and then I fit them into this framework, which actually shows the level of the ecological relevance growing from this, which is less desirable, to this, which is the most desirable way to deal with connectivity and climate change. So basically here, when one planner or one MPA, one manager want to try to think about persistence, we should start from, he could take one of these approaches here in the far left, but then it's more desirable if you move forward towards that way, where you can actually accommodate more functional resilience. We can derive more functional you can derive better, inform better conservation objectives to identify critical sites, such as the ones which are ecologically resilient or the ones which are more well connected, right? So here it's, when I say analysis of dynamics, I mean basically here it's like quantitative methods where you can actually predict the spatial and the temporal variability of these features in the seascape, right? The qualitative recommendations are the ones which provide a poor recommendation, because you can actually not do much. Just tell me that I want to protect whatever you think is resilient without giving me an idea of how to map the resilience. You don't actually inform very well. So let's see then how my framework fits with my recommendation. With recommendations, not my recommendations I found in the literature. So most of these recommendations for connectivity has been proposed through in a qualitative way, right? It's over 50%. And then we have just better, some few new studies, mostly new studies, start thinking about how to integrate these methods with the marine reserve design. And then when you see the results for climate change, this pattern is a bit worse. I have a lot of guidelines which provide me only qualitative recommendations, almost 75%, and then just sharply decrease towards that way. So I then, based on this, building on this framework, I started then proposing better ways to deal with connectivity first and then climate change. This is another chapter of my thesis, when I integrate multi-species connectivity, habitat quality into marine reserve design. So this was published this year in Ecography, and the objective is to propose one approach for marine reserve design, accounting for functional connectivity that takes into account multiple species and habitat quality. I'm going to explain you what is the relevance of this work. So, what you see, this is my seascape, and those are my coral habitats, right? As you can see, some corals are much closer to each other, and others are much further apart. So when I just have a look at this seascape, I can think that those reefs are more likely to be connected because they're closer than others which are much further. But then when I actually simulate and include the biophysical drivers of what interact to actually connect these reefs, I can see that, okay, is not just the distance is the only thing to think about here. So You can see that some reefs might be a little bit further, but it's still highly connected. Of the reefs, they don't have any connection at all. Another thing is also, it's another challenge issue when you start thinking about ecologically meaningful ways to incorporate connectivity, is that actually some reefs might be connected for one species, but might not be completely disconnected for other species, because the spatial ability for a species is very quite large here. So we might also include this, put this into perspective. The other thing is actually some reefs might be also, there is some importance here, because disturbances also interact with the structure of the seascape to also as well change the connectivity patterns. So in this paper, I deal with all these variables, all these challenges. The idea here is because MPA planners might be interesting, for example, to protect some areas which provides lots of larvae for other areas, right, which is this approach. But other planners might be more interesting, for example, to see, I want to protect areas which links source to sinks, areas which doesn't provide any larvae. Basically, damaged areas subjected to disturbances, which actually needs larvae. Or maybe MPA planners might be interested in protect areas which works quite well isolated, because they self-replenish, all the larvae come from there. So the methodology of this study, then I did this biophysical modeling where I included reproductive strategies for 4 different life history traits. And then I built this probability, connectivity, dispersion matrices. And then I integrated this with a habitat spatial model. This habitat spatial model, I use an additive approach to measure disturbances from local to global scale, like fishing, coastal development, thermal stress, sedimentation. So all these stressors act in synergy additively to then interfere in the amount of larvae released by each patch, right? The idea of this then was to integrate all these 2 different remote sensing to map my habitat quality and my biophysical modeling to then identify source reefs, which are the ones that provide more larvae, stepping stones, the reefs which are like corridors, and self-persistent, the reefs which are self-replenish. So these are some results. I can see my connectivity is clearly visible across these 4 species in my study area. So incorporate the habitat quality, reduce the reproductive output of many of my reefs. And there is a spatial disagreement. There is a spatial mismatch between areas which are important to provide larvae, the ones which provide function as a stepping stones, and the ones which are self-persistent. The key findings of this study is that first, I demonstrate one ecologically meaningful way to formulate connectivity objectives. Second is planning for multiple species results in mixed results. So we should be aware that planning for one species might not be a reliable surrogate for other species. Also, including this pattern of disturbances across my seascape has consequences for the connectivity metrics, which reflect in the spatial priorities, right? And this study then represents a holistic approach that enhances the design of functional network of MPAs by providing proven proxies for persistence. Let's move on now for my climate change chapter. So, similarly to what I've done for connectivity, I'm doing for climate change now. The idea is proposing one approach for marine reserve design that includes explicit information on historical and future warming impacts. This is under review currently +1. So to investigate the role played by MPAs in times of climate change, there is this framework which gives me the disturbance pathways when you assess effects of climate warming, right? The idea here is that these blue boxes are supposed to decrease, while these red boxes are supposed to decrease the intensity. So basically there is a disturbance from the water is getting hotter, And then you have a reduction of the coral cover and the fecundity, and this interferes in the interaction with in the competitive interactions with macroalgae, all promoting this shift from coral dominate to we all know this from a coral dominate state to an algae flash dominate state. But also climate warming acts as well to cause coral mortality and increases then the bleaching events, right? Bleaching level stress, which then contributes to reducing connectivity because we might have healthy leaves much further apart if there is habitat patches which has been bleached in the between. So then, basically, how MPAs could then affect this and minimize this, mitigate these impacts. So MPAs could act here locally because if I reduce the local stress, I might reduce the overall stress because the global scale stresses I cannot manage. And MPAs could also provide larvae to recolonize bleachy areas. So I interpret this disturbance pathway, and I interpret mostly in two different ways. One is here, where impacts of global warming are not lethal, are sublethal, and then here, where impacts of global warming are actually causing mortality, right? And this, I came up with this thermal stress regimes methodology. So here, I use data satellite of sea surface temperature from the history. We use the satellite climatology for 25 years. This is monthly data. And then I use the global circulation models to predict sea surface temperature for the future, 90 years in the future. So I use all this data to reconstruct my climatology for all my reefs in Brazil. So this is, for example, one example. So this is one particular location. So I have in red here, which comes from the observed data, which the satellites actually measure. And this is the projections showing then my annual maximum, in this case, just for simplification. I fit this regression analysis to calculate the rate of warming from these two different time series or time slices, right? To then come up with a measure of chronic stress. Similarly, I would like to compare, and then I use the same information, but now I calculate degree heating weeks, which is a reliable predictor for global for coral bleaching. And then I also evaluate the degree heating weeks from my two time series, right? So degree heating weeks, just to give you one brief introduction, it's first it has been the level of degree heating weeks, which is shown in this axis here. It's linked, it's very reliable predictor because it's linked with field bleaching data. So degree heating weeks equal to 4, which is half here, you can expect already some bleaching. Degree heating weeks is equal to 8, mass coral mortality, so means lots of damage. So as you can see here, some reefs might not reach this level here in Brazil, but actually around that time, you have to see some. I put the scale of this graph goes to 16 because some of my reefs actually reach 16, which is something, I don't know what's going to happen. So I use this information to fit them a logistical function accounting for different responses to corals to different levels of stress. And then I measure the acute stress. So now I have achronic and I have acute, right? From the past for the future. So I combine these four informations to delineate my thermal stress. So this is, for example, 3 of my 16 potential combinations. One is, in the first row, it's the observed data, and here is the projected data, right? The global circulation models. So I use the top and the bottom deciles to give me the high and the lowest level of stress. So here, in my observed data, in this, for example, particular regime, I have low chronic, low acute, both observed and projected, which means this area it provides the best likelihood to persist because it's a historical and a future thermal refugia. But those areas, for example, it's actually currently it's a thermal refugia, but this area is actually projected to face high level of stress. So in this case, the management requirement could be let's reduce local stress because because we can't control that. But other areas, sadly, are actually suitable only for thermotolerant species because they're all facing increased stress, both the past and the future. I then provide this framework which provides how to formulate conservation objectives to achieve my climate change goals. So here in this X, I provide both a chronic and acute, right, from low unto high projections, and in this axis the observed, right, from again chronic, this row is chronic, this is acute, from low to high. The idea is that we might require those areas here in the bottom corner, more areas inside the MPAs, and this should be under no-take areas because it's the areas I care the most. And if I move it on that way or that way up here, I might then reduce the amount of, the numbers are indicative, but the idea is that when you move it from that way or that way up, which you allow some sort of stress, you might reduce then the coverage required by MPAs. And eventually, you swap from no-take to multiple use, because then you just want to control the level of local stress. All these ideas are described in this paper. Hopefully it's going to come up online. Anyway, so I'm joking. It's already revised. So the idea here is that I classify my thermal stress regimes in my study area. So what I would like to highlight here is that my reef is in the north, in the far north, in the extremely south, here, are the ones face some levels of mortality, and reefs in the center are all types of thermal refugia are actually in the center. Some key results of this paper then. So coral reefs in Brazil have warmed and continue to warm by my measure of chronic stress. The bleaching level stress, which means acute stress, are expected to actually increase significantly in frequency and intensity. I also propose a methodological template that address specific warming-related variables to develop conservation objectives, which are more informed, right? And I also show the value of combining retrospective information with future projections. Because what? The big thing of this paper is that we cannot just measure thermal refugia in the past and assume that this is going to happen in the future. The pattern is completely, there is no agreement between these things when you actually measure them, right? So don't assume that what has been happening is going to continue to happen in the future. This approach also considers that different management requirements are needed to address climate warming. Let's now move to my final chapter, which is the integration of biodiversity, connectivity, and climate change in marine planning, then to provide some value of setting multiple conservation objectives. So this is to be submitted. This I should know. Okay. The idea here is that let's explore, when I pick up the findings from all the other chapters, and I see if I can see some interactions between different sets of objectives. When I say set objectives, I mean biodiversity, connectivity, and climate warming. So I'm going to give you a few more how I measure these interactions. So basically then I use the findings for my connectivity, where I derived objectives for sources, stepping stones, and self-persistent reefs. And then my climate warming as well, like I just mentioned. My objectives for thermal refugia, all the types, the area is supposed to be disturbed, and so on. And then I also introduce here, I develop better objectives for biodiversity, right? Like the ones traditionally systematic conservation planning deals more often. And this includes ecosystem types, threatened and endemic species, and also functional diversity. I'm going to give you more now information about the biodiversity because the other ones come from the previous chapter. So I then, considering these three data sets, I refine my objectives from my chapter 2, which is the first one I presented today. And then I re-examine the performance of my MPAs. And then I build scenarios for MPA expansion. And when I did this, I did this individually, and then I see if I plan for connectivity, how well I do for climate warming biodiversity. When I plan for climate warming, how well I do for the other both. When I plan for biodiversity, what is the impact on connectivity and climate change? That's the interaction. So the distribution for biodiversity, I use reef fish species as a surrogate. So I classify 400 reef fish species according to these three attributes: body size, maximum depth, trophic category. And then I formulate the objectives in the way that species which are large, very shallow, and coral-reefers receive the most demanding objective. I need more area inside the MPAs. While on the other far right, I have the less demanding ones, which supposed to have less decreased vulnerability to threats. When I also plan for biodiversity here, I also incorporate zoning in this approach, or MPA types. So part of my objectives could be achieved by no-take areas, and the other part I allow a more flexible type of MPA. From this pool of 405 species, I select endemic and threatened species because that's the one which we care more about. So I use this logical way to provide, to set up conservation objectives, which comes from 30% of their distribution range for non-endemic species which are vulnerable in the Brazilian National Red List, which has been just updated, so it's quite fresh. And then critically endangered, where the highest conservation objective is for critically endangered species, which it's endemic and of a very restricted range, right? I also allow some variability in the ratio between no-take and multiple use areas. So here I want everything by no-take, and here I'm more flexible. When it's non-threatened but endemic, this could be achieved by any type of MPA, regardless, no-take or multiple use. So when I go against my gap analysis to redo the same thing I did in the beginning, I see that more interesting results. So the objective achievement varies significantly according to these three sets of objectives. So biodiversity, MPAs in Brazil for coral reefs does quite well for biodiversity, but even though I still have species with zero level of achievement, which means even that special coverage massive, I still have 0% of objective achievement for even biodiversity, which biodiversity is the one who has been guided more often in conservation planning, and in Brazil it's like the same. Connectivity, then, we don't do performally that well, so this is a frequency density plot, so I have lots of conservation features for connectivity in the bottom of this graph, showing low level of achievement, and the maximum is 65. And for climate change, I have this bipolar pattern with some areas subjected to disturbance here, and types of thermal refuge here are unfortunately in the bottom of this graph. Let's then have a look. So I'm gonna show another result here. Interesting is that when I expand my MPAs to achieve all my conservation goals for climate change, connectivity, and biodiversity, and I compare this with the boundaries of my MPAs, I did this Misfit analysis where I showed that, for example, here are the number of reef locations, right? I use maximum reef zones, sorry. It's a marine reserve design tool which gives me the importance of each reef to achieve all my goals. So this is the result to achieve all goals, a well-balanced set of objectives. So this is if I categorize my reefs, right, according to the level of importance to achieve all these goals, comes from low to high, I see how the intersection of this with my MPAs. For example, when I intersect with my boundaries of my no-takes, I see that I have like 15% of the high priority areas inside only, and I have as well lots of low priority areas, like a little bit more than 15%, which is like well distributed into these three levels of importance. And then when I see the multiple use, the same exercise, but the output for the multiple use, I see that I have a very high level of misfit because lots of my low priorities are covered by multiple use areas, while less than 40% of my reefs are are covered by multiple use and have high priority to be in multiple use areas. So overall, 22% of my reefs are adequately protected, which means covered by the right type of MPA. So some summary of these results. So synergies between conservation objectives is quite variable. You might be aware of that. So you might limit the total conservation benefit of planning just focus on one set of objectives. MPAs in Brazil provide sufficient protection for a large number of biodiversity features related to coral reefs, but fail significantly at meeting objectives for climate change and connectivity. This study also highlights the shortfalls in the existing MPAs and demonstrates the value of setting multiple objectives from the beginning of conservation planning and provides insights for MPA planning elsewhere. Now let's move to my final considerations. So this is the concluding remarks of my thesis. So the first one is, given that the recommendations for incorporating connectivity and climate change lack some practical and meaningful applications, my thesis is that stronger methodological frameworks will operationalize their integration and improve the outcomes, the conservation outcomes in the sea. The second thing is the key aspect of this incorporation is better formulating conservation plans, or conservation objectives, which means planned by ecologically informed parameters in the initial stage of conservation planning. Planning considering a full range of ecological effects and that are modulated by connectivity and climate warming process, and the spatial and temporal scale over which these effects occur will enhance the conservation outcomes. The idea is that we need to take a more holistic and comprehensive approach when we look at these things, and just don't assume we are fine and that's the way to go. That's some outputs of my PhD. So I have 3 publications from my thesis directly related to my thesis. This one is under review. The last one journal to be to be submitted. I also gave some oral presentations. One of those, 3 of them was international conference. One in the Coral-Reef Symposium in Cairns, the International Marine Conservation Congress last year, and also the International Congress for Conservation Biology this year. Another publications you can check on my ResearchGate profile if you want to check out what I've been doing. And then I'd like to acknowledge also my institutional support from Brazil, of course, my fundings from CNPq, also from Brazil, and James Cookie, ARC, all my supervisors and collaborators, Pressey, of course, was fundamental for bringing me back to here and spend 4 years. The Conservation Planning Group, the people who works with him, close, Rebecca, thanks so much. We have been working closer. Also other collaborations, which is sort of fundamental for this work. And thank you so much for mostly my family, which is my biggest inspiration. Also many friends I made throughout these 4 years. Thank you so much, everybody, for listening. And I'm here for questions. Thanks.